So in this video, we're going to look at two more aspects of ions, and that are successive ionization energy and the size of ions. What successive ionization energy is when we keep removing electrons. So remember, ionization energy is the energy required to remove an outer electron. Successive ionization energy is just when we are removing the second or the third or the fourth electron in an atom. So if you look at this picture here, we already have an aluminum ion. Instead of having 3 valence electrons as aluminum typically has, this one only has 2. Now we're going to remove one of those electrons, and therefore the ion will now become 2 positive, right? And of course, every time an electron is removed, we have to add energy because we are overcoming attraction between the negative electron and the positive nucleus. Every successive ionization energy, so after the first, when removing the second or the third or the fourth, this time even more ionization energy is required. Every time that we remove an electron, we need to add more and more energy. And that's because of that first piece of Coulomb's law. When the difference in the charges is greater, then the attraction is greater. So you can see if we're looking at sodium here, sodium's first ionization energy, 495 kilojoules per mole. To remove that second electron, it jumps up almost 10 times. Now, you don't see that large of jump when moving from the first to the second ionization energy of magnesium. But then you do see a very large jump when you go from the second to the third ionization energy. And you'll see that pattern keeps going with aluminum and silicon, that you don't see a huge jump until with aluminum, the 4th ionization energy, and silicon, the 5th ionization energy. And that is due to what electron you are removing. When you are removing an outer electron, it takes a certain amount of energy. But once we start to remove what would be considered a core electron, the amount of energy required is much larger. And that's because the shielding electrons completely changes, and therefore that Z effective jumps up drastically. Right? If I'm looking at, let's just say, sodium, removing the first electron, you would have 11 protons in the nucleus. You would have 2 electrons in the first energy level, 8 electrons in the second energy level, and that 1 electron in the third. So what is the Z effective of sodium removing that first electron? Well, you would have the number of protons minus the number of core electrons, so the Z effective is 1. Now, after I remove that first electron, now look at what happens. I would still have 11 protons, but look at the number of shielding electrons now. That's only 2. Z effective is 9. Huge jump in Z effective, so therefore it takes much more energy to overcome that attraction. So let's write down basically a summary of what I just said. Successive ionization energy always increases, and you will see a large jump when you are removing core electrons because Z effective increases drastically. Okay, Z effective changes because those number of core electrons changes drastically. We have a whole nother energy level that cannot be used as as shielding electrons. So you can often predict how many valence electrons an atom has based on when you see a very large jump. If I did not know how many valence electrons an element had, but I see a huge jump at the fourth ionization energy, I would know that removing the fourth electron is removing a core, therefore it must have 3 valence. And as we know, aluminum does have 3 valence electrons. So that's successive ionization energy. The next related topic to ions is a trend in ionic size. So what happens to the size of atoms when an atom gains or loses electrons? So you can see from the picture here, when we go from a sodium atom to a sodium ion, it gets much smaller. And that trend will always happen, that the positive ions are much smaller than their parent atoms, the neutral atoms that they come from. And the reason why is because when you lose your valence electrons, you lose entire energy levels. You have the same number of protons pulling much less electrons, and therefore the ion is much smaller. Right, we would have a greater attraction between those outer electrons and the nucleus. The ion is much smaller. And as expected, we see the exact opposite happen when we form a negative ion, when we form an anion. Negative ions are always larger than their parent ions. And you have the same idea. The same number of protons are now trying to attract even more electrons. But there's a second reason, and that is that there is more electron-electron repulsion. You can see in the forming of the chloride ion, we're adding an extra electron to the same orbital, the same p orbitals. And once we do that, we know electrons are negative and like charges repel. Those electrons get further from each other, and that increased repulsion is also partially responsible for the increased size. So then if we were to take a look at kind of a scaled periodic table here, we would sort of see exactly that trend that we just looked at, that these atoms, I should say, these positive ions, lithium, beryllium, the metals form positive ions, and we can see that, yes, they are quite a bit smaller than the atoms that they come from. And in fact, the higher the charge, we can see that this aluminum is 3+, the higher the charge, the even smaller the ion becomes. And conversely, when we have negative ions, right, negative ions are larger than their parent atoms, because of that increased electron-electron repulsion. And the more negative the ion is, the larger it does then become.